more reasonable in his behavior. Okay, ladies and gentlemen, we are going to explore that at a very basic level right now, and we will return to agent-based modeling next time in a big way. So, ladies and gentlemen, what I'd like you to do is to go New Model, and this will be called SD ABM comparison, side-by-side comparison. We're going to build a little model which is going to allow us to compare the behavior of an agent-based model with the behavior of a system dynamics models on a side-by-side basis. Okay. Okay. So we're going to say the model time units, ladies and gentlemen, will be years. Okay. And we're going to say finish. Okay. Here we go. Okay, ladies and gentlemen. Now, I'd like to go to projects, and I would like to go and do something that's very familiar with us. We're going to create a first order delay, and we're going to do it with a certain chance per unit time of leaving, as I've used the term before, hazard rate. Okay? Here we go. So, going to main, we're going down main. Okay, and ladies and gentlemen, go to the palette, go to System Dynamics, and we're going to drag in a stock, and this is going to be a stock of susceptible, and we're going to add a stock of afflicted. Okay, people who are afflicted with some health condition, and we're going to have a flow between them. And I was not artful, but I'm going to say becoming afflicted, and as you know, I need to nicely match it up, and so I'll drag this over there till it's connected. Okay, and I'll frob these locations so that you can see them here. The number susceptible, ladies and gentlemen, will start at 10,000. 10,000. Okay, and the number afflicted will start at 0. And I want this to be a first order delay so that each year people have a probability of roughly 2% per year to go from susceptible to afflicted. So how would I do that in a principled way? Well, let's add a parameter. We're going to call it probability, or we'll call it affliction hazard. How do we like that? Affliction hazard. Okay? And it's going to be what? What value? 2% per year, so 0.02. That's rough because it compounds, but we're going to connect it up to becoming afflicted. And what else does becoming afflicted depend? Number of susceptible. If there's no susceptibles left, there ain't nobody who's going to become afflicted. Okay, becoming afflicted here, the formula for it is going to be what? Susceptible times or divided by? Times, indeed. A hazard rate is a chance per year, ladies and gentlemen. The units, if you have a unit of a stock that's, say, persons, the unit of the dimensions of the flow is going to be what? Dimensions per unit time. Dimensions per time. In this case, time is year, right? So it's going to be persons per year. So whatever the formula is here, we need it to be of units, persons per year. This is persons. This has got to be per year, right? And remember, it's probability per year is what this is. If we divided by it, we'd get all messed up. The flow would be of units, person divided by 1 over year, which would be person years, which doesn't make any sense. Okay, ladies and gentlemen, partly I'm telling you that because students sometimes mess that up in the exam. Okay, so what are we going to see? Well, let's go elaborate this slightly more. Let's go add a graph, here we go, a time plot. Okay, and ladies and gentlemen, the value of this time plot here, this is going to be susceptible, so this will be stock time plot. And we're going to add in a data item that will be called susceptible. And I'll call it susceptible SD. You'll see where I'm going with this. And its value will be this dot susceptible. Okay? And initially it says display up to 100 latest samples. For our purposes, that will be fine. Okay? So what did I do? I added in a time plot. I called it stock time plot. I added in data, said value, susceptible SD, and its value is given by the value of this stock. This refers to main, and so I'm asking about the value of the susceptible stock in main. What will I see if I run this model now? Will it be a straight line down? What will it be? It will be, ladies and gentlemen, curved. Okay. Let's stop at a time. I'm having some misgivings about those initial settings because I actually would like to see it for small numbers. Ladies and gentlemen, let's go back to that model and let's have it report it, display up to 200 latest samples, and the time window will be 200 model time units. That will let us do it for a bit longer. That will be useful. So I went up here, 200 latest samples, time window 200, and I'd like you to set, for the experiment, ladies and gentlemen, it to stop at specified time 200. So what did I just do? To go over that again, I went to the time plot. I went down to the thing that said here, data update, and I said display up to 200 latest samples. I went to scale and I set it to 200 model time units. This says how many data points to show. This says over what time window. What's the width of the time window? In this case, they happen to be the same because it's updating every year. Great. And then what did I do, ladies and gentlemen? Then I went to the experiment and I told it only run it to 200 years. Stop at specified time under model time. Are we okay with that? Ladies and gentlemen, let's run it. Let's let her rip. Okay, here we are. So we see this most distinctly curved fashion. All right, here we go. Good, ladies and gentlemen. Okay, now we're going to do something that breaks us out of our mold. We're going to do something that will follow us through the remainder of the course. Okay, okay, ladies and gentlemen, I would like to go to the model. Save your model. Save early, save often. It's a good principle, particularly on Linux where it crashes sometimes. Okay. I'd like you to right-click. I'd like you to say New Agent Type Person. Person with a capital P. Okay? Good. Okay? Okay. Oh. Bad things. Okay. Thought I mumble. Okay. Ladies and gentlemen, person with a capital P. We've just added, how did I do that? I went here, I did new agent type, and I declared person. Okay? I don't know why this is not recording. No. OneLSD, ABM 3. Okay, here we go. Boom. And start recording. Boom. Okay, ladies and gentlemen, so we have this model here with a first order delay, affliction hazard 0.02, 10,000 people starting susceptible, 0 people afflicted. We have this susceptible times affliction hazard. And ladies and gentlemen, we have a time plot that displays it till time 200. and we set the experiment to run to time 200. Okay. Now, we've just added new agent type person. Now, here we're going to do something different. We're going to go to Palette, and ladies and gentlemen, I'd like you to go down to the Pictures area of the palette. And you'll notice in the Pictures area, we can add in a depiction of a person. Now, I know your imaginations, for some of you, run wild when you look at the options here. Some people have a particular affinity for forklift trucks. We are going to add in, let's make it a patient. Here we go. Okay, here's a patient. We've added in a depiction of the patient. And these will actually be really useful in adding in visualization soon enough. For today, it's just going to be kind of a placeholder. Ladies and gentlemen, here we have a person represented, and we are going to go into main, back to main, ladies and gentlemen, and we are going to do something which again is unprecedented. So we've just defined a theory of personhood. The theory of personhood here is perhaps singularly simplistic. The theory of personhood simply defines the fact that person is associated with a visual representation. So now we're going to add, that's our theory of personhood, that's our theory of personness. We're going to add in a population of people by going to main, and we're going to drag in person to main, and we're going to call it population. Now, to be fair here, I could say a population of agents of size 10,000, but the software engineer in me revolts against that most unpleasant prospect. Revolt why? Because we're hard-coding a value that we may wish to change, which commonly would need change. And much of software engineering is about protecting us from the undue effects of common changes. We want to build a structure that can easily tolerate common needs changing. So we're going to drag in a parameter called initial population size. And what sort of population, what sort of type do you think this will have? Okay, so we're going to actually make it an integer. Amount is an interesting idea. I believe it's used for continuous quantities. So it's going to be an integer, and by default its value, unless we specify it, will be 10,000. And we're going to use it, ladies and gentlemen, for this population here for the initial number of agents. So the initial number of agents is going to be this dot initial population size. Okay? Secondly, we're going to go to the System Dynamics palette, and we're going to hitch it up to susceptible so that the susceptible here also begin with that same population. This dot initial population size. Perhaps you see where I'm going. Perhaps some of you anticipate already possible results. And indeed, I am bent on comparing the two. So, ladies and gentlemen, what did I do? I added in a parameter. I did it from the System Dynamics palette, but I equally could have done it from the agent palette, which we'll be exploring with some alacrity. So this initial population size parameter has a default value of 10,000. Its type is int because it counts the number. It's a discrete quantity. The initial population of the stock is given by this value of this parameter, as is the initial population size of this population. You notice, ladies and gentlemen, for this population, this is extremely important. If you look at it, when we first created it, I did not emphasize, but I did so in a neglectful fashion. This needs to be a population of agents. So when you drag this in, initially it may have looked like this after you typed the name, but you need to make it a population of agents. This needs to be selected, and then you'll be able to specify initial number of agents. Otherwise, it represents, ladies and gentlemen, just a singular agent. Okay? Okay, ladies and gentlemen. So here we have our population. I'd like you further to do one thing for this population so we can see it writ large in front of us. I'd like you to go to population, and I'd like you to go down. You'll notice I click on population, and if I go do that, I'll view there's a thing called initial location. I'd like you to click in the specified point, and I'd like you to do the following. I'd like you to say uniform, that's a draw from a uniform distribution, between 0 and this dot space, and remember autocomplete is your friend, space width. For y, does anyone want to prognosticate what I'm going to put here? Space height, indeed. So ladies and gentlemen, for x, uniform, this is a draw from a continuous uniform distribution with minimum value 0. I could have said, to be more explicit, 0.0, so it's clear it's a double precision value. We could have done that, and it's to indicate it's continuous, and the maximum value is space width. Okay? So we're going to place these individuals around the space that's allotted to them. And if you go to main, you can find how wide the space is. It turns out to be 500 height, 500 width by default, but we could change it and expect this to change with it. Okay, ladies and gentlemen, build your model. Now, this model is currently complaining of an error. It says initial population size is not expected but is used, and I am looking at where that is. Okay, so let's see why that is. Okay, it looks like it's actually, let's try this. So is this in fact hitched up? It is hitched up there. So that's an interesting thing. I don't remember ever seeing that error before. I think it's asking us to put a link here between those two, which is an unusual prospect in my view. So maybe we have to put a link like this. That would be a most peculiar thing. I'm going to ignore that error, which I may do at my peril, but is not used but is expected. Okay, so is it because of this? Yes, notice this X here is not used, but it is expected. Okay. Sorry? I think you need to get rid of this. Oh, do I really? Oh, yo. Oh. Okay, well, any logic exists with limitations. Okay, initial population size rather than this. Thank you, Janelle. Ladies and gentlemen, I'd like you to run this model. And, ladies and gentlemen, what are we going to see? What lies before us? There's a lot of people there indeed. Okay, ladies and gentlemen, for the sake of our eyesight, and indeed perhaps of our sanity, let's make a copy of this. Copy, and let's paste in a new one, and let's call it population size 1,000. Okay? And its initial population size will be 1,000, ladies and gentlemen. I'd like you to run it now. And what you see now will be a more pleasant aesthetic prospect. Okay, but you could see the number here getting smaller. So we're going to, you'll notice there's some dynamics of this system dynamics model, but not a lot else going on. So I'd like to quickly, with post haste, add in a bit of dynamics here. We're a bit behind, but we can finish it up if we're focused. I'd like you to go to population. I'd like you to go to palette, into the agent area of palette. Better yet, we could go to the state chart area of the palette here. Okay? Either one, agent or state chart. I'd like you to drag in a state chart entry point. This is going to be called health state chart. State chart entry point. I'd like you to create a state here. And this state will be called susceptible. I'd like to create another state, and this state will be called what? Afflicted. And ladies and gentlemen, I would like to create a transition betwixt them. And that transition will be named. Anyone? Becoming afflicted. Ladies and gentlemen, how did I do that? I went and I dragged in a state chart entry point and I named it health state chart. I dragged in a state called susceptible. I dragged in a state called afflicted. I then dragged in a transition, which I call becoming afflicted. This transition will occur at a specified rate per year. And guess what this rate will be given? By what will this rate be given? It's this affliction hazard. And wherein lives that? Where does that live? It lives in, yes, Maine. So, ladies and gentlemen, the rate is actually Maine dot affliction hazard. Oh, affliction hazard. Affliction hazard. Okay? Ladies and gentlemen, this is going to be a probability per unit time of this agent going from one to the other. Do you see that? So each agent here, remember, I told you, a system dynamics model is organized by state. We count the number of people in different states. An agent-based model will be organized by individuals, each of whom maintains their own state. Now, ladies and gentlemen, we're just about done. There's just two more elements we have to add, and it's very small. Go to Maine, if I may ask you to. Go to population. And I would like to go down in population to where it says statistics in population. And I'd like to press to add a data item. And it's going to be called count susceptible. This is going to be a statistic over the population, ladies and gentlemen. What sort of type of statistic will it be? A count, a sum, an average? A count indeed. Ladies and gentlemen, the count here, we're going to ask for each person in turn. It's going to be named item. You could see it by looking at this. It's called item. Each person in the population is going to be named item. We're going to ask, are they in a certain state? And what state are we going to ask, are they in? In what state are we going to ask, are they located? Susceptible indeed. And to do that, for technical reasons I'm not going to go into right now, but which will be familiar to those of you who have seen static members in Java, this will be person.susceptible. Susceptible with respect to person. Because after all, we might have susceptible deer, susceptible cattle, susceptible doctors, and in any logic, each class can have its own sort of states that have overlapping names with other classes. So this is susceptible with respect to person. So we're going to ask, are they in that state? Finally, we're going to go up. So what did I do? I went here. I scrolled down to statistics. I added a statistic, called it count susceptible. I left it as count, and I said item.instate person.susceptible. The final thing I'm going to do is you go up to this time plot, and we're going to add in one more item here that will be called susceptible, and guess what? ABM. And in order to get this, we're going to say this dot population dot count susceptible. How did it know to count the susceptibles in the population? Whence did this come?
From the value we gave it.
Yeah, we just told it how to compute in the statistic for the population the number of susceptible. All we're doing here, ladies and gentlemen, is using that. So what did I do here? I went to the time plot. I did a plus to add it in. I called it susceptible ABM, and I said this dot population. I'm referring to this because that's the thing that holds the statistic we just added, dot count susceptible. Ladies and gentlemen, that's all. Who would like me to show what I've just done? Who would like me to dwell? Yes. Okay, which part?
Sure.
So here we added.
No. Okay, no. Like, to actually run.
Oh, let's run it. Yeah, I share your enthusiasm, particularly since we have 1 minute left. Okay, here we go. Ladies and gentlemen, we're going to run it. Let's run it full tilt. Ladies and gentlemen, where are the two lines?
Overlapping.
They overlap, ladies and gentlemen. They're very, very close. In fact, if we went here, we went view, we could go zoom in. And you'll see here, this is the number from the ABM, and it's exhibits some fluctuation, does it not? This is the number from the SD model. I'll change it one thing, ladies and gentlemen. Ladies and gentlemen, we could change one thing, which would be the nature of that transition. I won't do it here because we're out of time, but I would note this is a rate per year. We also have the opportunity to set it to be a timeout, a fixed timeout. That timeout could be drawn from a distribution, for example. So we can leave after amount of time given by drawing from a distribution, or based on a condition, based on a message that reflects interaction with other agents, or when this agent arrives at a certain location. This is the vocabulary, ladies and gentlemen, the A through Zs that we're going to be using, we're going to be learning in the next few lectures. Okay? So, ladies and gentlemen, a comparison side by side of the most simple forms of each model. Again, this is the Dynamics model organized by state, where each state keeps track of the number of individuals in it. The agent-based model, keeping track of individuals, and each individual is in a certain state and keeps track of their state over time. Each of those individuals could have different states. They could have different parameter values if desired, although they all shared them here. But in the simplest form, we can get very good approximations of the aggregate model on the basis of from the aggregate model of the agent-based model. But we'll see that sometimes they can diverge, and radically so. Okay, so two simplest versions here. We have a population of agents, and that population is evolving over time according to a state chart with a fixed hazard. We will expand on these building blocks next time. Thank you very much. Okay, I have one point of great regret that I must share with you. A faculty meeting was announced for my department, mandatory, in 3 minutes. So I'm going to have to reschedule today's office hours. I will do so within the next 2 days. I will have an extra set of office hours shifted from today beyond Thursday's office hours. I know some of you were hoping to meet with me, and I apologize for this. It's a point of some seriousness with what's called a collegial case involving promotion. So I have to go to it today. It was a very recent announcement, but I will send times for a new meeting probably tomorrow. Okay? So thank you very much. I apologize for having to step out now. Thank you for your patience, and I look forward to seeing you at the latest by Thursday.